is yours.
Thank you for that. I couldn't hear you clearly, so your volume was really low. I wonder if you can hear me.
Yes, we can hear you. Don't worry.
Okay, that's good. Well, thank you so much again, Farad and Adrian, for your invitation and the kind of introduction. Following the previous talk, really it's my pleasure to share our work in the past couple of decades in terms of how autonomous systems or robots working with the human operators in the area of symbolic telepresence technologies here in terms of AI, autonomy, and digital reality for successful operations. I'll start with, in terms of where we are, in terms of the evolution of those technologies and methodologies for us to integrate those technologies to address some of the teleoperation issues. And also I'll give an example in terms of those technologies, how they are integrated into an exercise for test and evaluation. So first of all, trying to move this, minimize that so you can see clearly. As we know that AI and robotics technologies are the two representative fourth industrial revolution technologies identified by World Economic Forum. That's where we are. Everything now about AI and autonomy, robotics, etc. Then when we mention industrial revolutions, let's review quickly about how those technological transformations changed how we live, how we work, and socialize. First of all, in the beginning of the 18th century, with the introduction of machine power, we really moved our human society from agrarian one to urbanization. And 100 years later, with the second industrial revolution, industrialization with representative technologies of electricity, airplanes, mass production, etc., we are entering into a modern world. Then right now, we are in the third digital revolution, with electronics, internet, we are connected together now. Geographically, we are in different cities. However, in terms of time, we are together through the internet connections. So with other technologies such automation, etc., we are embracing globalization. So we are together, and also we are entering into the fourth industrial revolution. We are in the same human cyber physical space through the internet. I highlighted the three technologies I'd like to talk about here in terms of AI, autonomy, and mixed reality. We are empowering human productivities and capabilities. In the meantime, if we implement the chips in our human brain, we are not only embed technologies into our society, but also in our human bodies. So that will help us to address the limited cognitive capacity issues, because as this image shows you, over the past 3 million years, human brain capacity has gone up only about 2.5 times. However, as we know, the technology advanced in a much faster pace than us. So it helps us also to increase our cognitive capacity. And then let it reinforce the book. What the book tells us about singularity is near, because our capabilities evolves from physics, chemistry, to biology, then brains, and technology. Now we are at the fifth epic stage in terms of merging of human intelligence and machine intelligence together. Example with the chip chips implemented into our human bodies. So that tells us at this stage, we are really as one of the pioneers of AI or internet, like Licklider pointed out in the early of 60s last century, like human computer symbiosis technologies becoming a reality. What that tells us? It tells us, the AI autonomy or digital reality enabled social technical system becoming a symbiotic system. So it allows us to control a swarm of drone with mind remotely. So technologies increased our capabilities and capacity, but also in the meantime, it increased the complexity of the human machine system. Then what consequence? So this slide shows you one of the Boeing's study result about causes of the accident for human aviation. The two bars tells you about 100 years ago when our society started aviation, the cause of accidents primarily about 8% due to machine causes. But 100 years later, even 20 years earlier, 2000, beginning of this century, the ratios swapped. So with the complexity and also the limited human cognitive capacity, majority of the basic cause of the accident are due to human errors. But why? So this is for manned aviation. But how about for unmanned aircraft systems? So that makes us to think about for teleoperated unmanned aircraft systems. When we remove human pilots from the cockpit into a ground control station, what happened? What we should consider? If the human operators have the same interactions with the machine, with our counterpart, as what we used to be in the manned aircraft, because it changes our modality and sensation, and also how to design the ground control system. And then what technologies can be leveraged for performance augmentation. So that's all the questions. But before I answer those questions, let's review what the challenges or issues we are facing for remotely operated autonomous systems. First of all, we all know we have time delay. And then also, if we sit in a cockpit as a human pilot, you can see something. You can see your working environment. If you see something coming, another airplane coming, you can avoid that, right? We also have radio communication, some delays, etc. So that's all examples about teleoperations. But control, right? We don't have direct control like you sitting in the the cockpit. If you're sitting in the ground control station, then missed altitude deviation because you don't have the same sensation, same cues to remind you where you are, and other things about sensor, engine power setting, etc. And then in terms of the human machine system, right, as we point out, the cockpit elements are different from ground control station element. Then what will affect our sensation or perception, etc. Because we are in different locations geographically between the ground control station and the unmanned aircraft system. Then how about the human-machine interface? In terms of if those cues can provide us, let's say situational awareness in terms of visual cues, auditory, tactile cues, etc. And then associated with the physiological concerns in terms of if we have overloaded visual cues but unloaded auditory tactile cues, and others in terms of the shift, in terms of fatigue, etc. And also we don't have same working environment, then how we can to sense those noise and temperature, etc., in the air or in the remote environment when we sit in the ground control station. So those are examples of teleoperation issues. There are many. I just give you a few. So to address those questions or issues, we basically went back to see fundamentally what the manned aircraft when human pilots interact with a manned aircraft, like sitting in the cockpit, you interact with the aircraft through the cockpit as the human-machine interface. Three basic components: human operator, interface, and machine. And then we need to be intelligent. Our system needs to be intelligent, both human and machine, to understand what's happening in the task domain, in the working environment. So that's why you need to have world model of the working environment and how machine works. You need to have machine model and then task, what task you are doing there. So basically the system needs to have a situation assessment module. They need to also understand the human state in terms of their performance, engagement, attention, cognitive states, etc. So you need to also have a user model. The system needs to have a user state assessment module. Then through the intelligence, you compare the data between the changes in those two modules with built-in knowledge model, which is the adaptation engine, triggers the changes of the system to adapt to the changes in the task, machine, and environment, also user state. Then through human-machine interface, that module to interact, to inform, to provide SA, situation awareness to the human operators. So human operators understand what's changing there and how system adapts itself to the changes of the environment to achieve the maximum performance and build up trust. So that's the kind of the conceptual model of intelligent adaptive system currently we're trying to build up. Then to build that system, we also need to realize the nature of evolutionary stage of the system design strategy, as this chart shows us. For both front-end human-machine interface and back-end of automation functionalities. So at the beginning of the 50s in the last century, we focused on technology-centered design with a task model in terms of what we can dump to automation or technology and what left over to human if technology can do anything with it or with them. Later on, we realized, oh, that is not enough because we need to focus on what human skills in terms of the loss of the skills with increased autonomy. And then starting from the 80s of last century, we focused on human-centered design or user-centered design. Now you hear so much human-centered AI even, because you need to have both task and user mode in order to do that. But really, with what happened, in famous human factors disasters, for example, Boeing 737 MAX, right? With the increase in autonomous decision-making power of AI can ignore you. So really, when managing or designing system, it's not about technology or human themselves only. Separately, we have to look at how they interact with each other, how we design for relationship and manage that relationship, trustworthy, responsible relationship. That's why now, in the beginning of this century, we focus on interaction and design with the goal that to build up the trustworthy symbiosis technologies with two agents, intelligent agents, human and AI. So that's why you need to have all the models here, world model, task and system model, including both user and machine. So those methodologies has to be considered the operational context. Either you operate in air, land, sea, or in space on Mars. So for those safety and mission critical social technical systems, we have to manage the relationship. It's not only technology or human themselves separately. So we have to look at how they interact together to achieve the shared goals. So our approach has been reviewed by our academic partners, experts, industrial leaders, and then government authorities in terms of integrating AI agents to monitor and facilitate its interactions when human and AI working together towards the same goals. So trying to build up a collaborative, symbiotic partnership between human and technology, AI, autonomy, or digital media, digital reality technologies. And then our approach has been taken by NATO as a guiding principle to the design of development of the NATO standards. Remember I mentioned about sense and avoid? So one of the NATO standards about sense and avoid was guided by approach and also integrating technologies into the system, human system integration guidance as the leadership of the NATO military committee point out, we are building up capabilities, but we have to build that capability through process and trust. So NATO standards or methodologies are processes to develop the capabilities, but also need to build up trust. In order to do that, we also developed a trust model, which is a high-level system requirements for the human AI teaming, namely impacts. Because both human and AI agents need to have shared intention. But how I can understand or develop or my understanding about your intention? So your intention has to be measurable. That's why measurability is important through the performance, through the behavior, through the decision quality, etc. And then the system needs to be adaptive to all different elements of the human machine system in terms of working environment, in terms of the tasks, in terms of system, in terms of human mental states, and the attention, engagement, etc. Then communication has to be bidirectional between human and AI agents. So understand each other, and also through the transparency, we know how AI reached their decisions in terms of their reasoning process, in terms of the critical decision made, how, why. And then because we are connected through other networks, even for now, through the internet, how I can make sure I have the security to against adversary intent or attacks, etc. So that model was also the guidance for the United Nations white paper on human-machine interfaces in autonomous weapon systems, and also was featured on the SMC Society magazine. So it was well taken, and also the guidance for designing of technologies in terms of providing telepresence, situation awareness. The goal here is in the remote area, we teleoperate autonomous systems. How are we going to provide telepresence and to facilitate the teleoperation through AI, autonomy, and digital reality technologies? We fuse all the information, we fuse different intelligence, we fuse different technologies to provide situational awareness to facilitate the teleoperations. So here example, how we developed different technologies and integrate them together and test them out in an international teleoperations strategic challenge joint exercise in Australia. As you can see here, we have different autonomous systems controlled remotely by one single operator. Actually, the operator didn't control them. It managed those assets. It's a decentralized control. The autonomous system control themselves, and then we as human operator really managing those assets. So in terms of autonomous systems, we have 4 types of unmanned asset, basically for air, land, sea, and underwater. The image shows the access area, which was in one of the Australian naval base, in James Bay. And then a scenario for us to address the issue is the challenge of VIP engagement. Especially for us, if we operate overseas, we are not necessarily familiar with the international laws, local policies, regulations, or rules of engagement. And then as shown in the diagram at the bottom of this slide is the one of the processes for VIP engagement. As you can see, it's kind of complex, lengthy, and error-prone the process. If you remember, I mentioned about the human error is 8% of the cost of the aviation now. So that's something similar, really complex and lengthy error-prone process. So it's easily to for us lost the SA and also the costly mission failure. Then we won't trust technology anymore. If you ever watched the movie called Eye in the Sky, as shown in the image of the bottom right corner here, you exactly understand what I've been talking about in terms of processes, how the steps of the process can affect decision making. To address those challenges, we developed a technology called Authority Pathway for Web Engagement, APWE. The image on the right-hand side shows one snapshot of a state board for the transparency and explainability about how the process have gone through. So AI enable decision aid and provide that the SA to us. It enables the tasking authority to follow, the rules and laws and the processes to address the legal, ethical, accountability, and trust issues when we team up with AI-enabled decision-making tools. It intelligently updates the status of each step of the process and interact with the users in terms of new requirements, new information, new intelligence, and also it adapts the interface to different users based on their operational requirements. So it is an intelligent, adaptive system. And another digital reality technology we developed and applied here is AI-empowered virtual avatar with the effective cues to provide you real-time setup in terms of what's happening in the battle space. It provides narrative about machine reasoning and situation understanding for the complex working environment, which is the battle space there. Provide you explainability in terms of what's going on, what decisions made by AI or by other human agents. And its multimedia interface provides you the context of what happened there and why it happened and how you're going to make decisions in terms of command the teleoperator autonomous systems based on your workload. So it provides you intelligence, but also monitor your intelligence, your workload, and then intelligently communicate with you in terms of the situational awareness to facilitate your decision making. And then in terms of digital reality technology, so before we develop anything, we went back to reflect, okay, what's the nature of the technologies in terms of virtual reality and augmented reality, augmented virtual reality, and virtual reality. So we reviewed this continuum, mixed reality and virtual reality continuum. I had to pay respect to my PhD advisor, Paul Milgram. In the last 90s, he proposed this continuum and adopted by the society in terms of the nature of different technologies. So mostly we are taking granted, but really when we review the nature is really about if the environment is modeled or not. So for mixed reality or augmented reality or augmented virtual reality, the world is partially modeled. So that's why we took that approach. And also we reviewed the work we've been doing 20 years ago about the different immersive display technologies from 2D CRT to cave. And then in terms of its effectiveness, sorry, I'm gonna go back. And then what is most cost effective for us to develop? So we reviewed that kind of continuum in terms of immersive display technologies. That those kind of theoretical work guided us to develop this kind of control workstation as shown in this image. On left-hand panel, we have the narrative Citra app provided the virtual human in terms of what's going on, like your assistant or your associate helping out, explaining what's going on there, what's on the ground, what's in the air, what's in the space, etc. And then the web engagement APW, APWE, and under the virtual human provides you the processes, the SA in terms of web engagement process, and also to force you to follow international laws, RLEs, and standard operation procedures. And in the middle panel is the situation harmonies for the entire battle space. And also you have a workbook to play with your asset. You manage different assets in terms of all unmanned systems in the air, on ground, at the sea, also under the water. On the right-hand side, you have dozens of sensor inputs from different platforms, the sensors on all the unmanned systems. So it gives you kind of a curved display. You're not 100% immersed in that environment, but also you have the SA. In kind of you're playing a computer game, then you have the technology supporting you and augment your performance. So that's why it's a truly human AI autonomy digital reality teaming environment. So we did synthetic and lab trial exercise and the evaluation. Here is some feedback from the users in terms of our technology providing you transparency and visibility about the process when you work with AI agents, when you work with autonomous systems. And then because the intuitive of the interaction between human and the system, it provides you increased SA and reduced the workload, potentially human error, and increased the effectiveness of human autonomy teaming. The technology was regarded as the most trustworthy technology among all different command and control systems participating in the exercise. So the success was acknowledged by the commander of Air Force Research Laboratory at a plenary speech, Human Factors Economic Society Annual Conference in 2021. As you can see here, many different technologies we integrated together to test those technologies' operational utility, effectiveness, and interoperability, because they are coming from different countries and different services and environments. So that is how we applied our methodology and linked it with the technologies together to provide situation harmonies to telepresence and to facilitate the successful teleoperations. So with that, I don't want to drag you too much because before you're going for lunch, because you need food for your stomach. So basically, with that kind of story, we know that the system design methodologies has evolved, and we see the technology advancement, especially AI, and autonomy, digital reality, but how we can address the challenges I mentioned before, and then to ensure we have safe, responsible, and trustworthy type operation for maximize the public acceptance and societal impact. So that's this question really for our entire community. So I guess with that, I'll stop here and ready for questions.
Thank you so much, Ming.
I'll stop. You're welcome. I'll stop sharing.
In the interest of time and the food, as you mentioned, we can get one question from the audience. Yes. Yes. The question is that how important was having a person explaining the situation rather than diagrams?
That's a good question. Actually, at the beginning, we didn't think about
as a comparison, if you have any.
No, we didn't have a comparison. However, as I mentioned earlier, in terms of issues of that operation, we have, overloaded the visual cues, right? We have underloaded auditory and the tactile cues. So if we have the auditory cues to somebody to tell you something verbally, then it will lower your workload, right? We have limited cognitive capacity, so enhanced auditory cues to help you improve your situational awareness, reduce your workload, and then you maximize the performance.
So just to touch on that a little bit more, in the interface, it was on like an AI person there. But if you were to have that versus like a little symbol for Siri, for example, does that help the real human trust what the natural language model is telling you about the coordination of the mission?
Sorry, I didn't get it.
Maybe I'll take that offline and I'll drop you an email.
Okay,
thank you.
Sure. You're welcome.
Okay, I think this is very good. Thank you so much, Ming, again.
Enjoy your lunch.